In this chapter, we will look at the definition of the modulus of elasticity, the unit of measure, which is the Pascal, calculations for different spoke thicknesses and materials, a comparison of stainless steel, titanium, and aluminum spokes, and you'll see lots of math.
A topic not known for simplicity is the study of spokes' elasticity. We'll study the strain and what forces pertain, but stay out of the range of plasticity.
You may not have thought of bicycle spokes as being elastic, but they are, and if they were not, the bicycle wheel would not work. This chapter is about something called the modulus of elasticity. E is the modulus of elasticity, sometimes known as the Young's modulus of the spoke in question. And E is equal to the tensile stress divided by the extensional strain. Sometimes that's shown this way as sigma divided by epsilon. And that in turn is equal to this expression here, force divided by unit area, where F is the force in newtons being applied to the spoke from tensioning it, and A0 is the cross-sectional area of the spoke. That's the beginning cross-sectional area, and that in turn is divided by this expression here, where L1 is the length of the spoke after being tensioned, and L0 is the length of the original spoke. Let's look more closely at what's inside this box here, and we'll copy it down to the bottom to give ourselves a little bit more room. The numerator here, force divided by area, is, of course, a form of pressure. We honor Blaise Pascal and use his name. A Pascal is a unit of pressure, and it's defined as a Newton per square meter. The denominator of this expression here is really a percentage change, so it's considered dimensionless. The modulus of elasticity therefore measures pressure, and the units are in pascals. But wait, this sounds like stretching, and I thought that pressure was a compression force, so let's take a quick detour and explain that. Let's take one of the spokes from a wheel and put it under a microscope. Now I'm going to take that spoke and I'm going to examine its cross-section. I'm going to take that spoke and tension it, and in so doing I'm putting a force on it, either expressed as kilograms of force or as newtons, and there's my force. My spoke begins with a diameter of 1.8 millimeters, which is 0.9 millimeters of radius, and I get an area of 2.54 square millimeters. Now I can easily compute my pressure, force divided by area, gives me this expression. I divide that out and I get 46.3 newtons per millimeter squared. So we are in fact applying pressure to this spoke as we stretch it. Let's look at a simple graphic for a wheel. The wheel is laced up with stainless steel spokes of a length of 300 millimeters. Let's say they have a diameter of 1.8 millimeters. There's our radius, 0.9 times 10 to the minus 3 meters. And if we calculate the area of the spoke, this time in square meters instead of square millimeters, we're going to get this expression here, 2.54 times 10 to the minus 6th meters squared. L0 is 300 millimeters or 0.3 meters. I put 130 kilograms of force or 1,275 newtons on that spoke, and when I do, I find its length has increased to 300.75 millimeters. So L1 is 0.30075 meters. My spoke has been stretched 3/4 of a millimeter. If I put my initial cross-sectional area up here with this other data that I just calculated, then the data that's inside this box here is exactly what I need to plug into my elasticity formula. And let's put it down at the bottom to give ourselves a little bit more room again. Here is force divided by unit area in the numerator, and in the denominator, I have L1 minus L0 divided by L0. Reducing this down a little bit. So what this expression is showing me that in my denominator, I have a 0.25% increase in the length of the spoke as a consequence of putting the amount of tension I did on a spoke with a diameter of 1.8 millimeters. When I divide that out, I get a typically really big number, 200 times 10 to the 9th newtons per square meter. And 200 times 10 to the 9th newtons per square meter is 200 times 10 to the 9th pascals, or 200 gigapascals. And if we look at the literature, we find that that 200 is pretty close to the typical reading given for the modulus of elasticity of stainless steel wire. About 200. What I want to do now is compare the elastic modulus of stainless steel, as you see here, to some other common materials. In the next chapter, we'll come back and look at stainless steel in much more depth. Specifically, we'll compare stainless steel with titanium and aluminum for spokes that have the same cross-sectional area. Let's make another table and show the comparison here if I use different spoke materials. So we'll show the material, the modulus of elasticity of that material, the diameter, the cross-sectional area, and then see what happens to the spoke length as we go from 0 newtons to that much tension, and what will be the percentage increase in the length of the spoke. Put in the first line, which is stainless steel. We have a modulus of 200 gigapascals, a diameter of 1.8 millimeters, an area of 2.54 square millimeters. This is the length with no tension on the spoke, and this is the length after we have applied 1,274 newtons of force, and that is a 0.25% increase. That's the example we just worked out. Experimentally, I should be able to calculate the elastic modulus of a spoke material, because if I know the force that I'm putting on the spoke, and I measure its starting cross-sectional area, if I measure the length of the spoke or the percentage increase in the length of the spoke, then I can calculate the elastic modulus. Conversely, if I already know the elastic modulus, I can calculate the percentage increase in length that I should expect from applying a given force. Using this device here, I can put a spoke in it, measure its length, and then add tension to it and measure its length again, and then read the force applied over here on this gauge. In this particular device here, I can crank this up to 5,000 newtons if I want to, which is enough to exceed the tensile strength of the spoke. I have the capability now of measuring the elastic modulus of any spoke, of any material, of any diameter. Let's now look at titanium, sometimes used as a spoke material. It has a lower modulus of elasticity. There's my same dimension, the same area, starting with 300 millimeters. It's going to increase to 301.38, which is a decimal 0.46% increase in its length. Here's aluminum alloy, modulus of 70, same dimensions again, starting 300 millimeters and stretching that one to 302.16 when it's fully tensioned, which is a 0.72% increase in its length. Let's make sure we don't miss the main point of this, which is that if I start with 3 spokes of varying material, but they have the same diameter, the same cross-sectional area, and the same length when there's no force put on them, and then I put on a force of 1,274 newtons to stretch them, as the elastic modulus decreases from 200 to 110 to 70, on the right-hand side, both the length and the percentage increase go up. Let's do an interesting comparison here. Let's say I start with an aluminum alloy spoke with that modulus, and I start with a spoke that's 300 millimeters long. My question is this: what does the diameter and the cross-sectional area have to be to give me the same strain as I have above with the stainless steel spoke? When I grind out that calculation, I find that for my aluminum spoke to have the same strain as a stainless steel spoke, its diameter has to be about 3 millimeters with a cross-sectional area of 7.11 square millimeters. If you're talking about high-end wheels that are made for speed, then going from round stainless steel to round aluminum alloy is a bad idea, and here's why. The following couple of slides will give you a peek into some of the issues about aerodynamics that we will study in great depth later on. If we look at a flow diagram of air trying to pass around a cylinder like a spoke, we find that we have eddy currents behind the spoke because the drag coefficient of the cylinder is not very favorable. So I'm better off with a small diameter spoke than I am with a large diameter spoke because the drag will be less. Even if both of these spokes have the same drag coefficient, clearly the frontal area of the spoke with a diameter of 3.01 millimeters is more than the frontal area of the spoke with a diameter of 1.8 millimeters. Drag coefficient and frontal area will be discussed later in the chapters on aerodynamics. And let's just finish up this comparison by comparing the mass of the stainless steel and aluminum spokes with the same strain. My comparison is going to be stainless steel with a 0.25% increase and aluminum alloy with a 0.25% increase, and comparing these two cross-sectional areas. Now, for both the stainless steel spoke and the aluminum spoke, their respective volumes are going to be gotten by multiplying the cross-sectional area by the length, which is the same length in both cases. So let's walk through this calculation here. We start with the volume calculated as 762 cubic millimeters, which is 0.762 cubic centimeters. And here's our mass. If I multiply the volume by the density shown there, I get 6.12 grams. In the case of aluminum, I have a larger volume because I have a larger cross-sectional area, and I get this volume. When I multiply the volume by the density, I get 5.75 grams of aluminum. If we have 64 spokes, then we have a mass of stainless steel of 392. Aluminum would be 368. We have a difference there of 24 grams, which is about a 6% reduction in the mass, which is, for a road bike where you want speed and good aerodynamics, it's not a good trade. Now, if we're talking about a mountain bike, such as the aluminum spokes that Industry 9 uses, that's another matter entirely. There it's fine. And you can have a lot of fun adding some bling to your bicycle. Just for the fun of it, let's do the same thing and put in some titanium spokes and run through that same question. What does the diameter and the cross-sectional area have to be to give me the same strain? And when I work that out, I get these numbers here for titanium. Here's my same calculation for the mass of stainless steel, 6.12 grams. When I work it out for titanium, same process as before, I find that I need 5.93 grams of titanium. With 64 spokes, I have a very small difference in the mass, only about 12 grams, which is kind of a meaningless 3%. And looking at it again from the standpoint of aerodynamics, I'm obviously better off once again with the stainless steel spoke than the somewhat thicker titanium spoke. And for the reasons we've seen here and many others besides, this is why it is overwhelmingly better to use stainless steel in the wheels of most bicycles. It's absolutely a fantastic metal for that purpose and unequaled by any other. In the next chapter, we'll study stainless steel spokes in more depth, and you'll see how the elastic modulus of different materials directly affects the lateral stability of wheels.